So as we talk about what mass timber is, I just want to show you a couple of examples. First, I'll show you some glue laminated timber. And this is what the columns and the beams in the structure are made of. The layup is a little bit different with what we have in this building, but the idea is the same. In a glulam, you can see that individual layers of structural lumber are placed in parallel with one another. Resin is applied between the layers and pressed together to then make columns and beams of a variety of depths and shapes. The interesting thing with glulam, of course, is that you can use wood of varying strength categories in the manufacture of this material. So depending on the type of layup that's being used, lower strength material can go in the middle layers, and then higher strength material go in the outer layers for the tension and compression lams. So all of our beams and columns in the building that are made of wood are made of glulam. The other material that's featured throughout the STEM building is CLT, cross-laminated timber, and that's what we see in the various floor plates throughout the layers of the building. I've got a small block that just shows, again, a cross-section of the material here, and in this case you can see it's a 3-layer or a 3-ply CLT. You've got 2 outer layers that are running in parallel with one another, but then in that middle layer the lumber is turned at 90 degrees. So you end up with a product that's very strong, resistant again to lateral forces as well as tension and compression forces. And typically you'll see these laid up in an odd number of layers, anywhere from 3 to 9 layers. We've got examples that you'll hear from others throughout the tour of this building. We've got examples of different compositions of lams for various purposes throughout the building. I've also got a larger chunk of the material down here, which maybe makes the layers or the plies a little bit easier to see. So in this case, I've got a 5-ply cutaway section here. Now when the CLTs and the glulams are fastened together, typically installers are using these structural screws. Now this is a smaller screw, not the typical size of screw that was used in installing floor plates to the glulams. Those were anywhere from 12 to 14 inches long. But again, just a hardened structural steel screw that you'll see examples of again throughout the tour as we go through, in joining steel beams to CLT floor plates, as well as various railings and other metal plates to the CLT and the glulam. Now over here to my right is really the beginning of the structure. The first structural members that are placed in the building are the Glulam columns. So in this case what happens is the concrete floor is poured over, in our case, a series of concrete piles. And then you can see the steel base plate right here, which is embedded into that concrete. Now the steel base plate has a knife blade that basically comes up through the middle, and these glulam columns have grooves and notches that are cut out of them that slide right over that knife plate connector. Those are laid into place, and then steel pins are driven through prefabricated holes in the column. So you get, again, a fairly fast assembly on those columns, a rigid assembly, and an assembly that's manufactured to very, very, very tight tolerances. So from here we're going to go up to the second floor and look at some of the glulam and CLT beam to column and beam to CLT floor plate construction details. Now if we cross over through here, we'll be on the second floor of the North STEM building, where the construction detail is a little bit different. Now we've got a more conventional glulam column and glulam beam and girder, vertical or gravity frame, with the CLT floor plates supported by those glulam elements. So if you look here just above me, you can see one of the friction fittings in this case that's being used for a beam or a girder to column connection. And there's not much to see right now, just that thin band of metal. But in the exploded view, you'll be able to see how these pieces all come together to provide that fitting between horizontal and vertical elements of the glulam structure. Throughout the mass timber wings of the stem building, you'll notice a number of these X-shaped lateral bracing or cross bracing systems that are here next to me. These are custom fabricated in Germany just for this project. There's a fairly long lead time on them, couple of months. We've referred to them as Basista rods, so it's the lighter gray components that are fabricated in Germany. The X part in the middle comes from the mass timber supplier in Canada. But this system is designed to keep this building plumb and square and resistant to lateral load forces. So heavy winds, forces like that might try to take an otherwise plumb and square building and rack it, in the direction that the wind is striking the building. So you'll see there's tabs that come up out of the floor plate. Those tabs are then connected into these Basista rods. The full system is erected, and then there's another set of tabs in the floor plate up above. And the rods basically function as turnbuckles, just very large turnbuckles, and they have threaded fittings on each end of the rod, and they can be turned until the appropriate degree of level, plumb, and force is exerted on each portion of the building.
Here in the stem buildings, we used Clt Cross-Laminated Timber for our wall structures and our egress stairs. This was designed from a structural load point to use 5 plies, 5 layers of wood, in order to create the strength needed to support the building. The additional 2 plies that we used get us the fire rating that is required under the Michigan code of a 2-hour rating to support this stair. So basically 1 ply burns for each hour the building theoretically could be on fire, and that allows the building to maintain its structural integrity through the duration of any fire event, should there be one. This is a little bit different than what we did at the floor structures, which were typically a CLT is done in layers, odd number of layers, so they can cross each other to gain all their strength. On the floors, because of the large spans that we have for the labs, to create the open labs, there was concern of vibration as students worked and moved their way through the laboratory, and that causing distractions for learning. So we needed 3 plies for strength, but went with 4 plies in order to dampen that amount of vibration that was occurring. What's really peculiar about it is the 2 center run the same direction and the 2 outer ones run the same direction, as opposed to pure cross lamination. This was important also dealing with modular thicknesses and sizes based on the manufacturer's criteria of what their strength of every individual lumber has its own strength and weaknesses. And so we went into the bidding phase with 1 set of wall sizes and column sizes and beam sizes, and we had to revise that and tweak it a little bit to work with the standard fabrication sizes for the awarded contractor. That was some of the important things that we had to allow for flexibility in our detailing with where walls were placed and where things joined the wood structure, so that the rooms would maintain their sizes and we could deal with this fluctuation as the wood structure moved and changed. One of the criteria that goes into designing a 100-year building is providing for future flexibility for the university as the change in technology, change in education types, and change in use occurs. Here in the STEM wings, we thought about that, thinking that this double lab that we're in here now could be split into 2 labs, or the wall behind in this direction could come out and then you give a double lab in that direction. So in order to allow for future walls to align with the column lines and work with the modular nature of the building, we installed 2 beams up at the floor structure in order to leave a gap so that the plumbing and electrical and any utilities it needs to run can come down through and serve and get in and out of the building. What happens if we put the beam on the center line, you can see how wide the beams actually are, then you would have to jog the plumbing lines or the lines around, or make an extra thick wall on the floor above, and we didn't want to have to do that. So we split the beams. It made for an interesting bit of detailing when we come to the columns, but I think it's going to serve the university very well.